My name is Mantas from company Energy Advice, and today I will present the main functionalities of EA-PSM software for solar PV network design. So let's do a quick presentation of main features of the software. So to begin this, it will be good to get in touch what I'm talking about. So there are many functionalities regarding electrical network design of the EA-PSM Electric software. Main of these are like load flows analysis. Probably you all know this. Short circuit calculations, which are needed for like protection coordination, cable selections, and so on. We also have protection and automation features that allows to select the protection relays, their settings, so that they will work in a selective and reliable way. And there are many other functionalities which are important for distribution, transmission, and industrial networks maintenance engineers, also design engineers. So today during presentations we will try to cover some of them. So let's start from opening the software main window, and in the main window you will be capable to see single line diagram which I have created before the presentation, so that mainly we will concentrate on calculations and main engineering ideas, not on the drawing the single line diagram. So as I have mentioned in the presentation, we will more concentrate on solar network calculations, solar PV network related calculations, and one of the problem which engineers need to solve in practice is whether we can connect a solar power plant to the existing electrical network. So in this case we will analyze 5 megawatts solar power plant actually, and we will try to connect this 5 megawatt solar power plant to distribution network, which is 10 kilovolts distribution network, and we will assume that this solar power plant is 5 kilometers away from the substation of the distribution network. So first of all, what we need to analyze is voltage drops in cables, and also how our solar power plant will affect voltage in the substation sections. So to do this, we will use power flow calculations. So first of all, let's calculate power flows. And we can see that the existing voltage with the connected solar power plant, now it is generating 5 megawatts of active power, and also it consumes, in this case it consumes reactive power. So we can see that voltage in the substation bus is close to 100% from nominal. Nominal voltage is 10 kilovolts, as I have mentioned previously. So now let's assume that our solar power plant will disconnect. For example, due to short circuit, it can have we can expect it to disconnect suddenly. So in that case, we will lose quite a big generation source, and we want to evaluate how much this will affect the voltage. So let's go back to the voltage, so we can see it's 100% it was before, and now when I will repeat power flow calculations with solar power plant disconnected, I can see that voltage is 99.5% if we will round up to the bigger number. So voltage drop is 0.5%, and actually it is quite a significant impact on the voltage which we get from the solar power plant. So if we have this kind of voltage drop, then we have to look to standards like IEEE standard. They will specify how many this kind of voltage fluctuations we can have in the network in case we are talking about renewable energy power plants generators. Let's try to connect the solar power plant one more time, and let's start to change power factor of the solar power plant, because again another second thing that engineers need to calculate in this kind of systems is how much solar power plant will affect voltage when we will use power factor control, because solar power plant inverters usually they are capable of changing power factor. So let's enter minus 0.95. So this is our power factor, which we'll assume now. And let's evaluate how this will affect the voltage with the new power factor. So you can see when we consume power factor, voltage goes down actually. Instead of 99%, which we had here previously, now we have only 94.5%. And if we'll go look at our distribution section bus, so we can see it's 98.9%. So another a half percent voltage drop. So in total, we have about 1% of voltage drop. And actually, again, as I have mentioned, this kind of voltage drops, they are limited. If 1% is, for example, only 20 or 50, maybe this kind of voltage fluctuations can appear in distribution network, because this will have a huge impact on industrial consumers, also domestic consumers, which we have connected to this distribution network. So first a functionality which I have presented here now is power flows calculation. It is needed for evaluating voltage drops in the network. And another feature of this functionality is capability to evaluate currents in the network. So let's see, in this cable, which is used to connect our solar power plant to the network, we have some kind of voltage drop, which is over 4%. So, and also power losses. So power losses are added of two parts. So one is active and another one is reactive power losses. So in this case, if I'll put my mouse cursor on the number here, software will show that in particular this cable active power losses are around 166 kilowatts, and the reactive power losses are around 70 kilowatt. So power losses are quite huge. Actually, even 160 kilowatts, it will cause a lot of losses for solar power plant owner. So in this case, we might want to check how power losses will be affected if we will increase, for example, cable cross-section area. So let's open the existing cable and go to details. Here we will be capable to select parameters for the cables, and instead of the existing cable, actually you can see that there are many cable types in the library, so we can just select one step smaller cable diameter, but instead I will put two cables in parallel. So now we will have a bigger cross-section area in total, and this will allow me to evaluate how much actually losses will change with this kind of the configuration. So now I directly see that my losses are significantly smaller. Instead of 166 kilowatts, now I have 110 kilowatts of active power losses. What is more, my voltage drop instead of 4% now is only 2.5%. So this kind of cable configuration, where I have two parallel cables, 185 millimeters square each, allows me to reduce actually power and also voltage losses. Of course, these parameters will be also affected by current, which is generated from your solar power plant. So if I will reduce power factor to zero, because as I have mentioned previously, in solar power plants it is possible to reduce power factor to zero. The inverters have this kind of functionality. So then solar PV will generate zero reactive power. Current, instead of existing 304 amps, it will go smaller, and it's now 283 amps. Yes, and I can see directly that my losses are even smaller. It's 95 kilowatts now instead of 110 kilowatts, and my voltage losses are also a little bit smaller. Of course, not that much, because current changed only by, let's say, 12 amps. However, but my active power losses are reduced significantly, which is again an important finding, to see how active power losses and voltage losses are affected by active and reactive power balance in the network. So with this kind of software we can do this analysis, of course. Also, voltage will affect currents and all the parameters in the network as well, because mostly in order to save power, distribution system operator will try to keep a little bit bigger voltage than the nominal. In isolated neutral networks, they allow even a 5% bigger voltage. So I can also simulate this kind of situation by changing my transformer tap changer position. So I will set one step higher transformer tap changer position. I can see that this will affect voltage by 1.5%. Of course, all the loads like solar power plant will also affect the voltage, so it will be a little bit higher than nominal. Okay, so in this case, I see that my voltage is now 100 and almost 6% higher than higher than nominals by 6%. So this, of course, as I have mentioned, will affect currents and voltage losses. So power losses now are only 84 kilowatts. So again, from as you remember in the beginning, it was 160 kilowatts. Now we only have 84 kilowatts. So we have reduced losses by half actually, and also we reduced voltage losses by half, because at the beginning it was over 4%. So this is because I increased voltage in the network. The same power will be transmitted with a smaller current if I have a bigger voltage, and this will cause a smaller current, and of course, as a result, smaller losses. So all this kind of information can be actually easily evaluated, and it can give a systematic view for your students to know how these kind of things affect the network. Because if only you make hand calculations and you cannot evaluate the bigger network and how many factors affect the system, so then it is hard to understand and to get that systematic view. Also, you know that cables, they have capacitive currents, because especially in a medium voltage network, high voltage network, there exists capacitance between the cable conductor and the ground. So this kind of software allows to estimate that these kind of parameters as well. So for that, let's disconnect first of all only the solar power plant and just try to repeat the calculations. We will evaluate what kind of current flowing in the network by judging on our current angle. So first of all, current angle is measured from voltage angle. So it's difference of current and voltage vectors angles. So in order to be capable to evaluate this angle, we need to know what is the voltage angle in our main bus, and it is about 1 degree, minus 1 degree. So it's not the big voltage angle, because this particular transformer is not changing voltage angle at all. Its connection group, vector group is zero. So now we can judge that this kind of current, it is 85 degrees from the voltage angle, and it means that it is mostly capacitive. So we see that it is close to 90 degrees. However, there is some active part of the current, so which is created by our transformer no load losses. And if we will go closer to transformer, we will see that transformer consumes about half amp of current, yes, 0.5 amps, and this current is the same angle as our voltage, so it means that it is pure active current. And even if I'll put my mouse cursor on the power rating here, so I will see that it is 9 kilowatts of active power. Our transformer is consuming this even without no load connected. So this is transformer no load current, and we can see that it affects our line current as well. However, if I will disconnect transformer also, and I will repeat calculations, so now my voltage angle will move closer to 90 degrees. Yeah, it's now 89.1. So which means that now this current is even more capacitive. So mainly this current is flowing through capacitances between the conductors of the cable and the ground. one of the things which is important for practical application of this software. So if you will need to connect additional cable in medium voltage network in order to connect your solar power plant, so distribution system operator will ask you to calculate this current, because they need to know how much this current will affect the existing network. One phase short circuit current, it is called grounding short circuit current. Maybe it will be necessary to increase Peterson coil power and things like that to compensate this kind of capacitive current. So this value is also important for solar installations, and actually it's a must to evaluate this when you connect cables in a medium voltage network. So now we estimated, and we mainly worked with only one calculation feature. It is power flows, but as you can see, it gives a lot of actually interesting findings in the network, even with only this one functionality. So now let's start to use other calculation functions. So it is short circuits. Again, a very important feature. Every engineer need to calculate. Design engineers, maintenance engineers, from time to time need to use this functionality. So in software, we can calculate three-phase, two-phase short circuits, also one-phase short circuit, which, as I have mentioned, in isolated neutral network will be called grounding, and also two-phase with ground short circuits. So these are four type of short circuits, and they are defined by IEEE standard. Most common short circuit type is one-phase short circuit, but in order to select all the equipment according to worst case conditions, so we know that three-phase short circuit gives biggest short circuit currents, so we need to calculate also three-phase short circuits as well. So when we do calculations of the short circuits, we can actually analyze and look at the short circuit results in the whole network by just simply selecting any bus. I will show, and I will say that, for example, I will assume that short circuit is at particularly bus 4 in this case. So software will display me all the current values which are presented in the network in short circuit, and particularly that bus. So you can see that three-phase short circuit current is actually close to 7,000 amps. It's quite huge. Two-phase short circuit current is a little bit smaller. It's about 6,000 amps. And finally, the smallest one is actually one-phase short circuit current. And the smallest it is because this network is isolated, and actually this short circuit current, the only path for this short circuit current is capacitances, which I already mentioned. So actually in this kind of networks, one phase short circuit current will be very small. So what you can show for your students actually is how this current actually will depend, will look at different sequences or phase currents. So particularly what we see here now is zero sequence short circuit current. Yes, so we know that our protection devices will actually measure 3 times zero sequence. So according to this rating, we will be capable to select grounding protection equipment. However, for example, if we want to check short circuit current in A phase, yes, so we can see that in A phase, this short circuit current will be much bigger. It's 25 amps, because actually in software we assume that short circuit is going on in A phase if it is one phase short circuit. So all the capacitive currents from the network will go to this particular phase. And actually, if we will reduce number of conductors in the network which are generating capacitive current, so this particular one phase short circuit current will be also affected, because we will have smaller capacitive current. So you see, instead of 25 amps, now we have 21 amp. And it's mainly again capacitive. I can see this by a current vector, but there is some part of active current. Again, this is because of each cable they have losses, and those losses create active current part. So it's inevitable to have also active current in case of one-phase short circuit and isolated neutral network. However, if we will go to a grounded neutral network, here by the way connected with two transformers, I have a grounded neutral network. So in this kind of network, actually our voltage, our currents, in case of one phase short circuit current, will be much bigger. So you can see it's around 3000 amps. So again, this kind of simulation, it shows and allows to see how currents look in different networks, because this one is grounded neutral. So we have different phenomena in this kind of network. This one is isolated neutral. So again, we have different things in this kind of network. So with using the software, you can quickly simulate what if scenarios, and this will help you to allow actually how those currents will be different in different scenarios. Okay, so now let's start. Also, let's try to connect the solar power plant. We will make all the calculations which are needed for protection coordination. So these are power flows, short circuits calculations. Mainly, I need the three-phase and two-phase short circuit calculations. And now I can open this breaker. So here you can see it is a breaker provided. So we can go further on selecting protection relay for this breaker. So first of all, we know that our protection relay should not trip during normal operation conditions, which means that our protection relay current setting should be bigger than normal load flows current. So we can see that it is a normal load flows current is 267. So we already calculated this current when we're doing power flows calculation. And in the diagram here, it is represented by this red curve, this red line. Actually, I have the diagram of time and current axis. So on this diagram, I can work with protection relay selectivity. So for working with protection relay selectivity, I need to have information about all the currents, starting from load flows current. Then there is a short circuit current, which is depicted in this gray color line, and also I need to know information about my cable capability, because protection should protect equipment in the network, and cable is also need to be protected by the protection relay. So our relays should be capable to disconnect before our cable will melt down. So when we will work with protection coordination, we will evaluate this. So let's start from adding overcurrent relay, first stage. So we denote this relay as I more in the software, and most commonly we have to select this relay current setting, judging on the normal current. So as I have mentioned, it was around 268, but you remember that when voltage is changing, this current can go up. So we need to use some kind of sensitivity factor. So usually we use like 20%. Now I won't calculate the exact value, but I'll just simply enter, let's say, 320 amps. So this is one of the setting for overcurrent protection relay. It's pickup current. Then there is time setting, and in this case time setting is 20 milliseconds, so it is the minimum possible time setting that I can set. Actually, we will work on this further on when we will go back to that protection coordination chart. And also I will just select different curve types. So now I have definite time, which means that my protection relay disconnection time, tripping time will not be affected by current, but I'll just select normal inverse again by IEC standard. So we can see this is the protection curve of normal inverse over current protection relay. So in order to change time, I can double click on the curve itself, and I can, for example, enter 200 milliseconds instead of the existing 20 milliseconds. So I will see directly how this kind of curve is affected by changing the time setting. And actually we will change this time setting judging on the protection devices that are closer to the loads. So now we are working with protection in our substation panel. However, if it's, for example, industrial consumer, so industrial consumer will have a fuse or a breaker which protects their network and their loads. So our actually overcurrent protection device setting should be capable to work selectively with that particular protection device in the industry, in the factory, or in the solar power plant, for example, network. So this is the overcurrent protection device. As the name denotes, it protects our network from overcurrents. However, in order to increase speed of protection operation, we also have different types of protection devices. For example, in order to protect cables from short circuits, we can use instantaneous protection device. And for the instantaneous protection device, actually, I will use maximum three-phase short circuit current to select this protection device. So I see that maximum short circuit current is about 8150 amps. So let's go to the breaker again, and here we will add the second step for our current protection devices. So for this particular protection device, I will enter actually about the same current as maximum short circuit current. So I want this protection device only to be sensitive to short circuits that are happening in the cable, and even somewhere not at the end of the cable but closer to my relay. I won't change time setting here because it should be minimal. It's protection which works without time delay, and usually it is definite time. So I will also select that these two curves, these two protections should be connected. So now you will see that software will show both of these protection devices in one screen. So here this green one, this one is which we used previously, it was overcurrent protection device. Another one is instantaneous protection device which protects our cable from short circuits closer to our breaker. So now when we have this kind of picture, judging on this, we can directly see that our protection should not trip during normal load flow conditions, because this red line here, it shows 267, and we can directly see that our protection device setting is bigger. Then we have a cable capability curve, and we can see that this cable capability curve at all points is higher than protection device settings, protection device curve. So that means that in case of, let's say, any short circuit, our short circuit current can be like 6000 amps. So if we have 6000 amps, we'll go up into while we'll reach this curve, and we will see that after about half a second, our first stage of overcurrent protection device will send the trip signal to the breaker, and our cable will be capable to withstand this kind of current for about 8 seconds, so 8.5 even. So it means that our capable will be capable to withstand 6000 amps, and it will not melt, it will not break, and so on. Protection will just simply disconnect the short circuit current, and the problem will be solved. Actually, it will be a short circuit will be disconnected. Then engineers can look for solutions of the problem. It can be, for example, so some kind of a mechanical fault for the cable, let's say. Okay, so now we did protection coordination for this particular cable, actually. Now we can use software to check with this protection coordination, if this protection device and the protection coordination which we did will work as expected. So for that we use a relay coordination function, uh, actually a relay tracking function, and it is possible with this function to select a particular bus in the network. For example, let's select bus 4, and to simulate short circuit in this particular bus, so that we will be capable to estimate which protection devices will trip in this short circuit. Okay, so software now is doing the required calculations. So we can see that in case of short circuit at bus 4, actually we have several protection devices that are tripping. So for example, even this protection device here is tripping, and this is of course not required. This one is tripping as well. So we can now check why these protection devices are tripping in case of short circuit at different bus. So to do this, we need to be capable to put more than one curve in the same plot, so that to analyze selectivity. Yeah, so for example, just add the protection devices here. Yeah, okay, so I see that particularly that breaker, it does not have any protection device currently. Probably there is only the overcurrent protection device with zero current setting. So this was the problem. Actually, by using protection tracking functionality, we can notice any actually problems in protection coordination. Okay, so by increasing the current settings, let's see here. So in this particular location, I might want to, for example, I will even remove this protection device. And now, as I made some changes to the network, again, I can repeat protection tracking calculation to see how protections will operate now. Yeah, so I can see that now when I fixed all the protection settings, so I increased times where necessary, judging on the load flow currents. So now in case of short circuit at bus 4, yes, only one protection device is tripping, and this particular protection device is here. So software even shows the whole process. So at the actually at the beginning we have pickup, yes. So pickup is actually as we have noted, our protection device have some time delay, so this will take some time, and actually all these times are represented on this process diagram. So, but the important thing for us is that breaker open command was sent after 493 milliseconds after the short circuit, and the breaker took about 50 milliseconds to open. So after 543 milliseconds, we have our short circuit disconnected. So as we remember from the previous analysis, our cable will be capable to withstand short circuit current, maximum short circuit current, for over actually 8 seconds. So this kind of time is actually good for us. So when we do a solar power plant integration study, always we are asked to do protection coordination, actually, to calculate short circuits, because short circuit currents are not only needed for protection coordination, we need short circuit currents to estimate how powerful is our network. So if our network is having very small short circuit current, it means that it is not powerful, and we cannot connect big actually and powerful solar power plant, because it will affect our loads too much. So these kind of calculations are always required by distribution system operator in case we are connecting solar power plant to their network. So we also need to do protection coordination. Now we worked with overcurrent protection devices. However, a solar power plant, in order to work properly, it also have one more breaker actually near to the solar power plant itself. And here in this particular breaker, we need to have voltage protection devices. Usually we use under voltage protection devices. So in grid code you can find what time settings, what minimum and maximum time settings could be set for this kind of protection device. Usually these are let's say 800 milliseconds if our voltage goes like from nominal, so let's say 100 volts, yes. So nominal voltage phase to ground is 230, because here it's a transformer which reduces to 400 phase to phase voltage. So phase to ground voltage, let's say, if it's so small, yeah, so it means that there is short circuit somewhere in the network, and waiting some time, we can disconnect our solar power plant. But we cannot disconnect it instantaneously, because again, if we will disconnect solar power plant instantaneously after any actually fluctuation of voltage, so it will cause instability of the network, because we will lose power generator, and we will have to compensate that power from some other generation sources, usually thermoelectric power plants. They generate the biggest part of the consumed energy, so they will have to compensate this loss of power, and of course this can cause problems to the network. So we have calculated now power flows and short circuits, and we looked through actually mainly all the things that are required by distribution system operator regarding these calculations. Usually also distribution system operators, especially nowadays, they require to calculate harmonic flows. So harmonic flows is a similar functionality as power flows. However, it calculates not only 50 hertz current, but also higher harmonic currents. So if I'll do a harmonic flows calculation in this kind of network, and right away I can say that we have a harmonics source in this network, because solar power plants, they are connected through inverters, so definitely they will generate some kind of higher harmonics. I can even see and I can configure what kind of harmonics our solar power plant is injecting into the network. So now I have values recommended in IEEE 519 standard, which is the main standard for harmonic calculations. And this is for 6-pulse inverter, which are most commonly used in practice. So when I do harmonic calculations, I will have information about current and voltage harmonics. These are actually two different things. So let's see what are the current harmonics in the cable. So if I'll put my mouse cursor on the cable, software will represent me the histogram of several harmonics. So I can see that some of the harmonics are having red lines, red horizontal lines with them. Some of them are having green horizontal lines. So the difference between these two are actually limits, again specified by international standards. And if we have red line like 5th, 7th, 11 harmonic, they have those red lines. It shows that these particular harmonics are exceeding the permissible limit by international standard. And even total harmonic distortion, which is represented by THD acronym, so it shows that it is over the permissible limit. And our total harmonic distortion in percents of current harmonic distortion is 22% almost. It's quite a big actually current harmonic distortion. And voltage harmonic distortion in this side in medium voltage network is 4.4%. So if we will look to the network, it's 2.8%. So let's try to disconnect our solar power plant and see how much it will affect the voltage harmonic distortion in our network. Actually, this again finding is very interesting for distribution system operator. Yeah, so we see that now the harmonic distortion is significantly smaller. So which means that our powerful solar power plant is actually main source of harmonics in this particular network. We have some kind of harmonic equipment in low voltage as well, but they are much smaller in power and they are not causing so much problems. So it means that actually distribution system operator can ask an investor or design engineer to fix problems regarding high harmonic distortion, because it causes actually many practical problems for all the loads that are connected to the network. So with this kind of software, you can not even estimate the harmonics, but also find the possible solutions for harmonics related problems. And one of the solutions which is quite commonly used is three winding transformers, actually, to actually divide the harmonics from solar power plant in two halves. And by changing phase angles of separate harmonics, we can actually mitigate the total harmonic distortion. So I think I have the example for this actually three winding transformer prepared. It's the same network, just with a three winding transformer which divides a solar power plant in two parts. Yeah, so we can see, we can look at here. We have the same power, it's 2.5 megawatts and 2.5 megawatts, so in total it's 5 megawatts as in the previous example. And we have a three winding transformer with specifically connected windings. So if I'll open the transformer itself, I can go to connection type. So I can see that there are also phase angles between high voltage winding and low voltage windings. And these phase angles are selected so that they will change harmonic phases to be opposite, and when we will calculate the sum of those harmonics, actually they will be close to zero. So now let's calculate harmonics with this kind of the transformer. So we can see that in this side our harmonics are the same. It's about 22% as in the previous example. However, now if we look at this particular side, so we can see that our harmonic distortion, current harmonic distortion, is only 5.6%. So it's significantly smaller, like almost 4% smaller. And if I'll put my mouse cursor on the cable itself, so I can see that none of the harmonics are exceeding the permissible limit. All the horizontal green lines and all the horizontal lines are now in green color. And if I'll go to voltage harmonic distortion in substation buses, so I can see that it is only 0.8%. So with this kind of transformer, we solved actually harmonic problem, and we haven't used any filters, just change the phase actually difference of the separate harmonics when they sum up, so they are close to zero. So it means that there are various solutions. For example, this one is quite commonly used in India, in Asia, where they have a high temperature, high ambient temperature, and it causes harmonics plus high ambient temperature. It causes additional stress to equipment. So they use this kind of equipment to mitigate harmonics. In Europe, we more commonly use filters for harmonics. So again, it's possible to also evaluate filters with this kind of software. So what we look now is the main features that I needed and that are required by a distribution system operator when we are evaluating solar power plant installations. So to summarize, first of all, we need to know how to calculate power flows, because it is important to evaluate how much your solar power plant will affect the network. Then we need to be capable to calculate short circuits, because according to short circuits we select protection equipment, we select even the main equipment like cables, transformers, buses. Like peak short circuit currents can cause mechanical forces, therefore all the insulators should be capable to withstand those mechanical forces, and particularly short circuit calculations allows to get the required parameters for this kind of studies. And finally, it is harmonic flows, because solar power plant inverters, they cause harmonic distortion. We need to evaluate whether we should take some kind of actions to solve this harmonic distortion, or these harmonics are within the permissible limit, and we can leave them as it is. So these are three features, most important features that we need for solar power plant grid integration studies. And this kind of software is not limited to only these features. Actually, in industry, we can calculate something like R-flash, which is quite common. Motor starting, we have capability to analyze dynamic motor starting. which again allows to estimate how much time motor will take to start, what will be the starting current, and all these things we can evaluate with variable frequency drives, with self starters, so to estimate various decisions on how to make this kind of process to less affect the network. And DC network calculations, so again it's for solar power plants mainly. We can calculate and design DC networks, and also hydraulic calculations regarding water, gas networks, which is more for mechanical engineers. Finally, reliability calculations. So reliability calculations is important actually for electrical engineers as well, because various substation schemes are used in practice. For example, if we need to design network for nuclear power plants, so they require huge reliability actually of the network. So then we can design network and calculate what is the reliability of that network to actually to provide the power to the specific point, to the specific bus. So these kind of functionalities are also included in the software. However, they are more like for related to other topics. And finally, there are many functionalities regarding to calculations. If we're talking about solar irradiation features, so we have like solar irradiation modeling, which allows to calculate solar power plants generation. We can actually import data of solar power plants. We can specify what are the inverters used. For example, we can use something like this. I have 23 inverters, 25 kilowatts each. I can select some kind of solar power plant, estimate how many modules, how many arrays there are connected in series, and how many of them are connected in parallel. So let's say I will reduce the size for this installation so that to fit inverters data. So software will allow me to calculate what is the irradiation, of solar in that particular location. We can see how much energy our solar power plant will generate. Of course, energy, we have losses regarding to this, because there are losses in inverters, there are losses in modules. So we also can see losses and evaluate, for example, balance diagram, which shows what sizes of those particular losses, so like inverter losses, module losses, and what is the efficient power which we sell to the distribution system operator. So we provide the full list of functionality to do designs for renewable energy, but also it is not limited to that. It can be used to calculate distribution network, do protection coordination in isolated ungrounded neutral networks, also analyze industrial networks, as you can see here. So it's like typical industrial network scheme. We have buses and there are loads connected to those buses. It can be capacitors connected. For example, here it's connected through a filter, so to reduce resonance conditions, and so on. So it is a quick review of actually our software for power system design. As you can see, has a variable functionalities. Thank you for participating and for listening this short presentation. I hope that after this presentation you will have even more questions about the software, so we will be happy to answer those questions. So you can contact us actually through this contact information. Yeah. So thank you for participation one more time, and bye.